Good morning. I am Sheng from Sheng Memorial Secondary School. My team registration number is 60046. The topic of my project is called Wire in Magnetic Field. It is a study about the shape of a wire under normal force. From physics, I learned that a current-carrying wire in a magnetic field will experience a magnetic force as shown in this equation. Then at that moment, I wonder what would be the shape of the wire if the end of the wire is fixed. And from physical principle, it is known that the wire would enclose the largest area with the straight line joining the two fixed points. And using mathematical methods like the isoperimetric inequality and calculus of variation, we can show that this shape of the wire is a circular arc, and the proofs are included in my report. I decided to investigate the shape of the wire by considering the normal force acting on it instead of the area. And I would modify the proof of a catenary by choosing an arbitrary xy point on this coordinate and analyzing the force acting on the segment of this wire. However, although the proof of a catenary, the left force acting on this wire is the gravitational force and is vertically downwards. However, for the problem of my project, this wire would experience different directions of normal force, and I need to have a way to simplify the problem before I start my proof. So I have my theorem 1. On a continuous differentiable curve connecting two fixed points, every small segment of the curve experiencing a normal force proportional to the segment length, the total resultant force depends on only the distance between the two fixed points and is perpendicular to the line joining them. I used some integration techniques to prove this theorem. And with this theorem, I can get my main proof, which is theorem 2. The shape of the wire would be a circular arc. By theorem 1, I can simplify the total net force of magnetic force as this vector. And by analyzing the force, I can get this differential equation alpha, which gives us the equation of a circle as a solution. So the conclusion is that it is a circular arc. Then another problem arises, which is given the wire length L and the distance between the two endpoints 2a, then can we find the corresponding radius R? I divide the problem into 3 parts. For case 1, the wire forms a semicircle, and obviously R and L are one-to-one corresponding. For case 2, the wire forms a minor arc, and the equation relating L and R is shown like this. By using calculus, I can sketch the graph of L against R, and so that this function is injective. For case 3, last case, the wire forms a major arc, and the equation of L against R is this, and the graph is sketched like this. Again, this function is injective also. Therefore, the conclusion is that for a given L and A, there is always a unique corresponding radius for the circular arc formed. However, as the equations are nonlinear, and I cannot express R in terms of L and A explicitly, therefore, I decide to approximate the shape of this curved wire in another way. That is, using 2N rigid rods, which experiencing some normal forces to approximate the shape of the wire and to, approximate the configuration. This is the rod approximation part. Firstly, I consider a special case when n is equal to 2. That is, we have 4 rods, each experiencing a normal force. Each of the rod has a length of L over 4, and the distance between the two endpoints is 2a. By analyzing the forces acting on rod 1 as shown in this diagram, we can have theta 2 equal to 3 times theta 1, the equation 1, where theta 2 and theta 1 is the inclination of rod 1 and rod 2 to the line joining the two fixed points respectively. And by considering the horizontal distance of these rods, we can have equation 2, and combining we have equation beta. substituting b equal to 2a over L and x equal to cosine theta 1, we have a cubic equation in x. And by calculus, we can show that for a given b between 0 and 1, we can have a unique x corresponding between 0 and 1, 2. And therefore, we have a unique theta 1. And by equation 1, we can have a unique theta 2. Therefore, the configuration of these four walls can be uniquely found, as these two angles would determine this. Then, I generalize the result to two n rods. Each of the rod has a length of L over 2n, and the distance between the two endpoints is again 2a. By induction method and observing the relation between theta 2 and theta 1, I can get my theorem 3, which is theta I is equal to 2i minus 1 times theta 1. This simple and elegant expression. And again, theta I is the incarnation of rod y also. Using this, we can have, again, considering the horizontal distance, we have this equation. And as this summation of cosine theta I would lead to a high degree polynomial equation, which is of degree 2n minus 1. Therefore, I decide to use multiple angle formula to avoid this. Therefore, we obtain this equation. And again, substituting b equal to 2a over L, we have equation gamma. As the problem suggests, theta n would be less than pi and greater than 0. Therefore, by theorem 3, we can have theta 1 is between 0 and pi over 2n minus 1. So, my main purpose is to investigate equation gamma for theta 1 in this range. And using calculus techniques, we can show that this equation has a unique roots for where between 0 and pi over 2n minus 1, the graph of fn theta is shown like this. To check my approximation method, I used some numerical result to show that we put a is equal to 1 and L equal to pi, which is we have a semicircle case, and n equal to 100. That is, we consider 200 watt. Equation gamma would become this. And the numerical solution for theta is this number, which is approximately equal to pi over 400. Therefore, the chain would approximately form half of a 400-sided regular polygon, which can be inscribed in a semicircle, of course. And as a summary, a current-carrying wire in a magnetic field fixed at two endpoints would form a circular arc. My original problem is solved completely. The radius of the arc R is uniquely determined when given the L, wire length, and the 2a, distance between the two endpoints. There is one and only one possible circular arc formed. The shape of my chain of rods is also uniquely determined, since all the thetas can be found. However, as the equations are nonlinear, R and theta 1 I cannot find explicitly. In spite of this, it is still delighting and inspiring to use mathematical knowledge to solve a physics problem. For further development, after submitting the report, I have think about this. That is, I would like to generalize the problem to higher dimensions. That is, for example, what would be the shape of a surface experiencing normal force with its boundary fixed? Then what would be its shape? And also, of course, we can continue to solve for R and theta 1 explicitly. Try another method or... Yes, this is the end of my presentation. Thank you.